was the first module. It's still ongoing. There are a couple of things I still want to do.
Yeah, I think it was good for like, you know, it's not there wasn't too much information, so it would overwhelm us, you know. So I think it was like just the right amount.
Okay, very good. So have you guys read up on the homework assignment? There's a talk, basically it's text of a talk.
Yeah. Is due on Thursday?
Right. Yep.
Yeah.
All right, so it has to be one page, which includes everything, which includes your name, you don't have to even write your name, because when you submit on Blackboard, I can see who's submitted that. So it automatically, it shows me everything. And you don't have to put too many references, but you have to keep it on one page. That's essentially a requirement. So yeah, talk to me if you have any questions about that as well. So, and I shared a micro lecture as well last week. So hopefully that was also. So a lot of these things will build up as we go on towards the assessments. So we have a key paper review thing that's coming up sometime. I have to see the dates. But we are building some foundation so we can start thinking of, out of the box, I would say. All right, yeah, good. So, okay, so today I want to continue our discussion on the basic concepts of nanotechnology, even uh, touch upon a couple of concepts that I shared with you that are always sometimes challenging. So this idea of surface to volume ratio. So when you chop down bigger things into smaller pieces, there's one concept that overall surface area becomes larger and larger. You may have the same volume, but the it's the same volume when you put them all together, but more surfaces become exposed to the outside thing. So outside thing, maybe it's a reactant, maybe it's a chemical reaction, or maybe you are just dissolving uh, maybe salt and water. So that's a simple example. So if you think about it, if you have a big chunk of salt, I don't know if you have seen big chunk of salt. You know, they sell coarse salt at some places. Now, if you take two equal size of chunks and you put one in water and you dissolve it and you crush the other one into smaller pieces and then you dissolve it, which one will get dissolved faster? The bigger chunk or the smaller chunk?
Smaller one.
Yeah. Yeah, that's one.
The powdered version, right? And what's
Yeah.
the reason?
It's
What's the
smaller surface area.
surface area? But to scale that relationship, we talk about surface to volume ratio. So the thing you have crushed, it's the same volume, right? But now it's in powdered form. The volume stays the same. That's the important thing here. So when you make things, keep on grinding things smaller and smaller, what you call nanoscale material. What we are doing is we are essentially uh, bringing more surface for reaction to the outside world. And that means the reactivity of those things become much, much higher, very, very high, which means we can control or maybe lose control over those reactions in some way. So here's an example of a simple kind of calculation. So you start with the Rubik cube. So each so the big Rubik cube has 9 smaller pieces on each face. So if you think about it, that the whole Rubik cube is made up of cubes even inside as well, right? Although there is some mechanism inside, but let's just suppose it's all built up of. So the total number of cubes would be 27 in the large one. If I chop it, make it smaller with 2 by 2, that would have 8 cubes. If I chop off, just take one of those, that will be just 1 cube. Now, if I were to say, I say the surface the one dimension of a cube is say one, any unit, 1 centimeter, 1 meter, 1 millimeter, let's say one. So the total sides or total surface to volume would be 2 for the larger one, but as you keep on breaking it smaller and smaller, the number keeps on going up. So for example, the only one would have 6 as the ratio of surface to volume. And that gives us this high reactivity or very high reaction from those materials at nanoscale. Now, these are things which we are doing today, but this is not something new. If you think about it, that I have read up on things that how old is nanotechnology? They have found things as far as 2000 years old. And here's a couple of examples. So this mug, it's called Lycurgus cup. I don't know what's the historical or religious value, but it has gold and silver nanoparticles. So if you get the reflected light, it gives you a different color. But if you transmit light, you put the light from the back, it gives you another color. So they crafted and put nanoparticles in it that would reflect different wavelengths depending on what we uh, are we transmitting light or reflecting light. Just another example from 500 years ago, where were using nanoparticles to give different colors. So that's one of the reasons so many of those colored art pieces still maintain their color because the color is not painted. The color comes from the metallic particles that are put at those things. So nanotechnology has been there for for ever for us, for thousands of years. But now we have new tools. Now we can make new tools with which we can control those things. So the keywords for us today is we can controllably and repeatedly make those things at small scale. And as we grow further, you will see many, many more examples of how we make nanoscale things, how we make nanoscale material. Not just make it, how do we measure them? How do we characterize them that how they are when they are happening? So here's an example where it was made at 1 million times magnification in a transmission electron microscope. So I did this work, I don't know how many years have gone by. So what we had was a hole in a silicon chip, and and over time, going from A, B, C, over time the hole was shrinking. Can you see there is a very small thing written here on the top left of every picture? Is this number? Do you read what it says? It says 20 nanometer. And there is a small bar to it. I'll just highlight the bar. So this is 20 nanometer. So we use that scale bar to measure or uh, quantify what are the dimensions that we are looking at. So from here to here is about probably a 40 nanometer, and then it keeps on shrinking, goes down to 20 nanometer here in this one. So because I'm comparing this with the scale bar that the microscope is giving me for that dimension. Right? So that's the thing. Now we are at that stage in humanity that way we can controllably and repeatedly make things in the nano size range. Not just we can create them, but we can characterize them as well, which means we can measure their properties, we can see them, yeah, right? We can actually see their dimension. We can maybe see their uh, like conductivity in them. Now, conductivity, talking about very small current, picoamps, femtoamps that would flow through them. Now we have very highly sensitive detectors that can measure those lights that are emitted at for a femtosecond, for example. chemical reactions that happen too fast. So we have those detectors that are so fast, high-speed cameras, as we say, but these are super high speed. They can measure reactions or photons that would come out for even a femtosecond. So that's where we are today. Now, is it just in the labs or does it have a real world impact as well? So I came across this idea a few years ago, and this is still true. We, we like to eat rice, right? Rice, food. Have you ever count the number of rice in your bowl? No, it's almost impossible to count them. But we make more transistors every year than we produce grains of rice every year. Think about it. Our devices have like on average, we buy every year, every person buys maybe a cell phone. We buy gadgets, we buy the like headphone, earphone, I don't know, every month we buy electronics. So these electronics all have transistors, all have these nanoscale chips in them. So we are building these things so many, so fast, and we are measuring them. That's where we are. And it continues to grow. If you think about it, humans are continuing to grow, and the number of devices that make are continue to growing as well. This will be next module, basically, nanofabrication. That how do we make things so small? One can conceive have you guys made circuits, right? Everybody has made circuits on breadboard, right? Everybody has made maybe get a PCB made and put your components on it. You've done that, right? Okay. So you think about it. The first step in all those things is to lay out a circuit, right? So we take a paper and we draw a circuit. We say, okay, this transistor, this IC, this pin has to go here and there. We lay out the circuit. The same thing has to be done for making those chips, but their size is so small. You're not making a PCB here, and you are not doing soldering with your hand. So essentially, what we have to do is from visualizing, we create a design on our computer, but then that computer has to be translated on a chip. That's where that's uh, the beauty of doing that. That we can cram 32 billion transistors into maybe a half an inch by half an inch chip, right? That's the black microprocessor you have, maybe 2 centimeter by 2 centimeter. That's the what you call the major step of humanity that we have taken, making these 32 billion or so transistors on. Now, these 32 billion transistors are not on the whole thing. They are there are hundreds of those chips which are built on this wafer. So they may be even smaller than what I'm making right now, right? This is a 16-inch wafer, and the chip there is probably half inch by half inch. They made all of them are made in parallel. So many of them. Are you with me on this? I'll share a video on this this week on how do we what is the microprocessors especially and how do they make sense to it. All right, so let me just clear this and move on. All right, so
Sure.
yeah, go ahead.
I need to go collect like our trash so we can throw it out. So can I just turn off my camera real quick?
Yeah, it's okay. Don't
Okay.
worry. You can do that off and on. I don't see Amara and Rachel. I guess here.
Yes.
Yes.
Right. Let's have your cameras on. Sometimes you can turn them off when your dog jumps at you or your sibling runs around or your kid is yelling at you. But all right, so so impact, there's real impact. So this is an actual transistor, and we'll look at more examples and we'll uncover more things as we go. So we were making 50 nanometer channel device in transistors. On this is how an actual transistor on an IC looks like, right? So there are multiple steps that have gone through to make source here, drain here, oxide layer here, the gate size. These are things which we'll look at in nanofabrication and talk about that. All right. So we looked at it started in around the start of this century, but today we still have many challenges. So National uh, Nanotechnology Institute, they have come up with some grand challenges for us, that where we are still lagging behind, and we may have uh, some big breakthroughs that can come from nanoscale or nanotechnology. So, well, there are lots of discussion, lots of work that has gone on into those things. And we'll look at some of the examples today, some of them, not all of them. But you will see there is a common theme here. There's a lot of nano challenges which relate to us, that maybe it's our exposure to chemicals, maybe it's our things that we use, electronics, healthcare, which is the topic of this course also, that how can we interface biological systems or biomedical systems, or do something where we can diagnose things or maybe come up with therapies. So we'll focus a little bit more on bio side as we go forward. But let's look at some big questions or big ideas or big challenges that we have. So, for example, sensors, environmental sensors. Environment has a long-term impact on living systems, living things, on us, not just today, but our exposure to environmental things may give outcomes in maybe 5 years down the road or 10 years down the road. We still don't have comprehensive understanding of the fate of those things that can impact on our well-being. So why? Because those things may be either the things we are exposed to, they're too small, they're narrow scale, or the changes are so minute that we cannot detect them with the sensors we have today. So we need to make sensors small enough that can measure small changes. There's an example I like to give is, uh, you know, Braille code, right? The dots they have on, for example, when you're getting the elevator, the next to the number they have these dots, which basically a blind person can put their finger and they can feel the dots. Tells you for what floor you are at, 1, 2, 3. So those are small dots. If you are wearing a glove, we cannot feel those dots, right? So we need to have the same size that can feel those small dots. So if the changes are too small, our sensors have to be small enough so they can feel that small change in their values. So this concept called sensitivity, and you all will talk about sensitivity when we talk about biosensors, because those minute changes over time will result into toxicological effects. We say, exposure over a long time has resulted into some cancer or some other disease. So we want to measure environment with either things that are nanoscale or the changes that are too small to measure by big systems. That was when you talk about environment. Sustainable material and resources. We hear the word sustainable. Tell me, what do you think when you hear the word sustainable?
that we are able to continuously obtain the resources. Similar to how with oil, one of the issues that we saw just a few years ago is that a few decades down the road, we're going to run out.
You can run out. Yep. So now, sustainable. There's one idea. Okay, things that we're gonna use up, right? So that's not a sustainable direction to go. What other things come to your mind when you talk about sustainable?
Whether the mining process is damaging, not necessarily mining per se directly, but like the way to get the resources. Because while we may have a never-ending source of the thing, uh, let's pretend we do. By extracting the things, we could be either harming the location or ourselves.
So harming surroundings. That's another side to it. That the main source or the main resource may be uh, plenty, or we may not be uh, running out, but the activities that we do to use them may be giving out something which is bad. Anybody else? Sustainable, sustainability. What does it mean to you when you hear the word sustainable? So recycling. So we may be using something that's finishing, but can we use it in a way that we can re recoup something out of it, or recoup the original thing back, and maybe keep on reusing it. So sustainability has this concept of not just we have to uh, use the resources that don't finish, we also need to find a way that our impact is minimal while we do a process, and we should be able to recycle the things that we are getting any benefit from. But now we are finding that the things that we were throwing down the drain or burning in our cars, many of them can be done with either less harmful things or can be recycled. For example, hydrogen fuel cell. So all it uses is hydrogen. And what's the outcome? When you use hydrogen to run something, what is the outcome from that reaction? What is the product that comes out of that reaction? It's water, hydrogen, and air, oxygen. The product is just water. In the meantime, they will push the engine while they're doing that, right? So this is where new materials come in, new resources come in. That how can we do those reactions or do those things where we can either recover some things or recycle some of the things. Energy, transportation of goods, clean water, food, this is all a circle. There is the way we are going, by 2050, the population of the earth will double, but the resources will not double. The current resources are not projected to double by that time. They would increase maybe by 20% or 30%, but they will not be able to cope with 100% growth. That's where new materials. We have to come up with sustainable materials and resources with nanotechnology. Processes. Now, many times we take larger things, we chop them down. Give me an example of where we chop things down to use them for us.
Trees, paper.
Right? Paper, furniture that we are sitting on. We are using larger things, we are chopping them down. Can we take smaller things and build from smaller things up? Give me an example. Here's I would look for an example. Using smaller things and building things up. When we lots of bioorganisms, they make films. If you leave, I don't know, a water pond somewhere, you start seeing things building up. algae builds up, right? So small microbes, they come together and start building colonies. Many of those colonies we know now can be used to make hard materials. You can just grow those microbes and they can take the shape of structure that you put in. So you can put a dye in it, right? Like you want to make a chair, you can make a design of a chair with the dye and you can leave them. They will grow and it's been done. They can give you a hard material for whatever you want to use it for. So it's called, this is what the word here means, bottom up assembly. We'll talk about this also later on. So bottom up assembly, can we take those processes instead of chopping things down? We build from bottom up. That's another challenge for nanotechnology. Now, there's this impact on environment, right? So again, what are the implications on natural and global resources when we use uh, nanomaterials? Where are they going to go? Yeah, so we are building things, but we also have to worry about what will happen to them when we are done with them. So are they going to decompose or are they going to maybe start another challenge for us? So that's also concerned that what happens to those things once we are done with those. All right, let's do the next one. Health and environment. So think about it. What are the some of the issues we are facing today? Healthcare, exposure to things, exposure to unknown things. There are benefits. Don't get me wrong in of where we are today. Today, the human mortality is at lowest, no doubt about it. But still, we are exposed to new things. We There are genetic mutations, which we know that diseases are happening because of that, but we are still not being able to detect them. Yeah, Edgar, go ahead.
I was just gonna say, similar to like the BPA's that were discovered amongst plastic and putting them in the microwave, and now being replaced with BPOs, which have not been proven to necessarily be better, would not be affecting in a larger scale, but through time, and in a small scale, ends up affecting the human body.
Right? Yeah. So there's new materials which are benefiting us. So think about it now. If they hadn't done research, we would have been still doing the things the same way, right? So, but there is more things to do. Today, coronavirus, so COVID, it's very interesting that we get flu shots, right? We were getting flu shots. We knew flu existed. We didn't have a system for mass detection or mass deployment for detecting a flu virus or any other virus for that matter. While we know flu happens every year, flu comes every year, flu mutates every year, but we had not made things scalable that we could just use it against other organisms. That's a challenge. So it means there is something missing. Let me go to the next slide. That's where we are talking about this. I put some bullet points here, but we'll touch upon these because we need to think about it. And many of these are big questions for you as we progress. I want to hear from you what you have to say. So high throughput, sorry, wait a minute. Hold on. It's not aligned. Just give me a second. So high throughput, multi-analyte toxicology methodologies, high throughput. Like I take a sample, whether that's from my nose, where they are finding accumulation of virus, wherever it's from. Can we do high throughput? Means just just look for 20 organisms, multiplex, and get the answer in 2 hours before, now even today what's happening is they get tested and you wait for 5 days before you hear back. But that's wrong. We have nanotechnology that can do this, that have all the ingredients to do this within a couple of hours to give answer about it. But yes, that's why we are doing this. That's why we are talking about these challenges. We have to understand things that we build at nanoscale also. We can't just build, we have to know what happens to them once we are done with them. Now, when we make these materials, what happens to in whatever shape they are in the environment? A simple example, I worked with US Air Force a few years ago in Dayton on bio impact of nanomaterials. So in our quest for getting better explosives or better whatever chemicals, we are using nanomaterials in so many of them. But nobody has done any toxicological study on the health of airmen who are being exposed to those things every day. For a plane, they are putting paint or coatings on those planes which are easy to clean, which don't get wet, don't get, and they have very good aerodynamic properties, and they have nanomaterials in them. But nobody has done any study of what would happen to the airmen or people who were close to those things on their health. But this is reality. This is the challenge that we we don't have the toxicological assessment of those things. Hence, this area of nanobio where we want to do all this. All right. Now, impact of this work. Circuits, already I've talked about. We were making things with hands. We are laying down things, but now all we have to do is you make them on computer, and we still have to lay down, but what you are building that goes inside that black chip is what's coming from nanotechnology. What's inside these black things, your ICs. And we are making them smaller and smaller. We talked about industrial applications, right? So in industry, many times, a lot of times, they have to melt things to put them into a whatever they want to make, right? Maybe it's plastic, maybe it's metal. If you make them smaller, we can control the melting point. What this graph is showing, the diameters going smaller to the left. When you go into the smaller size, what we are seeing is the melting temperature is going down. Isn't that amazing? Because we always were taught that melting temperature is a constant for every material, right? But not anymore, because when you are going to that size scale, we are also finding new places where we can change the melting temperature of this material. Now, if you think about industry where they have to use so much energy to melt stuff, they can just crush it before they melt it. That can reduce lots of uh, cost. You can reduce lots of fuel. That can reduce lots of impact on the environment. Hi, Cecilia. I think you have two people listening in the same place. Oh, these are two students. All right. Oh, you guys live together. Okay, you're
No,
with.
we don't. We're just working on a lab.
Okay, okay, that's fantastic. All right, very good. So another example, colloidal solutions. So this is where, to think about it, we get some chemicals from hardware store or even drugs, medicine. They say shake well before use because things settle down. Things sit down in the liquids. Suspensions have, but when you make them too small, you crush them too fine, narrow scale, gravity have no effect. So these are colloidal solutions where if you leave a bottle of things, they would always stay homogeneously dissolved because gravitational force is too small for them to settle down. So that's where these paints and additives and all those things are making an impact. There's an amazing example of butterfly wings. If you put a butterfly, okay, we see different colors on the wings of butterfly, right? We enjoy beautiful things. But if you put them in microscope, electron microscope, and this is showing you magnification 220x to 5000x to 20,000x, we see nanoscale features. So by putting nanoscale features, we can get different colors from same material. Just by making features at small scale, we can play with the wavelength of light. We can play how light interacts with those surfaces of those structures. That's also which is already happening. We are making what you call metamaterials, where you create those structures at small scale to have different electrical properties, magnetic properties, different chemical properties by creating those nanoscale structures. Something that we have done, making cancer detection chips. So we flow in solutions, and this golden area is where we create these nanoscale features. So this is 20 nanometer to 30 nanometer features. And the red ones are shown as the cancer cells, blue ones are shown as normal cells. So those features can capture cancer cells, and we can identify or detect cancer at early stages with this kind of technology. All right, questions? I have, yeah, go ahead, Edgar.
Just when was this made, or because I never heard about it, and it's interesting.
We have a patent on it. We have done lots of work on this. Uh, just hold on a second. Let me pause a little bit. Take care of your question. Yeah, so this was, I think, 6 years ago we published this work, and there's been many variations of this which are being developed right now. But yeah, but nanoscale, and once you'll start reading up on some literature, you'll come across a lot of work that's happening on nanoscale interface with living things for early detection of diseases. And this is showing more on cellular level. This work is showing on genetic level, on individual genes. So what you see here, this is just a cartoon with black and green is shown the design of DNA which is coming together. So the golden things is DNA molecule taken shape of those specific square things, DNA molecules. And then they used these small nanoscale holes to flow DNA through. And this data is for the DNA going through, and they measured the current from that. We'll talk about this. I just wanted to, this the introduction module going on. So but we'll deal with this in much, much more detail as we go forward. So this is another example. These are DNA molecules. Now think about it. DNA molecules so small we can't even see with naked eye, right? It's 2 nanometer in width. But you can use, so this is a protein molecule. They're suspended in a fat layer, and they were measuring current across. So here's the current measured at 120 millivolt. And as soon as the molecule goes through this, there's a small opening here. So which means the resistance goes up, right? It gets like physically blocked. And they see drop in current. So these pulses are drops. And when you zoom in into one pulse, you see what you see here, like a current drop, current drop, and once the molecule goes through, current comes back to the base level. So they have identified different bases from that work. So think about it. We are looking at each individual base. So if we can sequence bases, and we know genes which are associated with diseases, for example, cancer, we can know exactly if a person has a cancer gene. So think about it. Just like we have free email addresses, free online space, gigabytes, free spreadsheets. On Google, you can make your Excel files, your documents. There's no more concept of paying for Microsoft Office anymore. In 5 years or maximum 10 years, we will all be able to get free genetic sequencing done for all of us because the equipment is there, devices are there, we know how to do it. It's just matter of time that somebody will find a way to market that and provide it for free. Because if we have all this database for all of us somewhere, it serves each one of us because we people can do research on dealing with those bad genes. They can work on living a better life so we don't get that disease for which we carry a gene. We'll have more discussion on this, but let's look at some more nanoscale materials. Carbon-based material is already making a big impact on our lives. So carbon is, yeah, we know carbon as charcoal, we know carbon as graphite, but when we are talking here is single layer of carbon, one atomic layer carbon, which is called graphene, but if you roll it, it becomes what we call carbon nanotube. We'll touch upon these things later on. And these are real pictures of carbon nanotubes. So think about it. This is 100 nanometer scale bar, so this is much smaller than that.
So for example, with that size and those properties, what are the carbon nanotubes used for?
This is a picture. They are already using to strengthen the strings of your records. Strings of your records, the material of the record itself. If you guys play any game which uses record, you would know those records have become super light now. They used to be heavy. When I used to play tennis, I don't know, 20 years ago, those rackets were damn heavy. Like to hold that racket, I had to like have huge muscle. But now those rackets are so they are stronger and they're lighter. They are using carbon material in those carbon nanomaterial to give that strength. So it's already, these are just few examples where there are already so many applications of carbon.
I barely noticed the name of this slide.
Oh, what can't you read? Oh, the racket?
Yeah, I mean, like it's basically this slide. It's basically what I asked.
Yeah. So we are using them in solar cells. We are using them in, bike racks, bicycles. Their uh, frames have carbon material in that, which makes them strong and lighter both sides. We have done some work in using carbon in concrete. So concrete on the road, for example, asphalt or sidewalks, they use concrete. Temperature, expansion in summer and contraction in winter builds up cracks in those. But if you put carbon materials or nanomaterials, they give them much more strength, much more breathing space to them, so they don't break apart so easily. So and there are lots of products which are already out there. So to sum it up, we already have day-to-day usage of these things, but we have challenges also where we want to go. We want to have get better and superior things in materials, in gadgets, in devices, in applications, right? And the promise is that we can tailor them from bottom up to our desires, and we can precisely control what we build, right? So that's the hope. That's where we are going. All right, questions? All right, so I'll post this lecture. I'll post a couple of other videos also. So, and we'll be getting into module 2. When I have the material ready, then I'll let you know that the new module is posted. All right. So till then, I'll let you guys go, and I'll see you guys next Tuesday. All right, very good. Thank you.
Thank you, sir. Thank you.
Yep.